Okay, so let's move on into chapter 5 and we'll talk about Newton's third law of motion. So kind of where we're going to go is first we're going to talk about what an interaction is and how it's going to require pairs of forces. And then Newton's third law is going to relate these action and reaction pairs as they're called. And then we'll just kind of sum up the chapter by just talking a little bit about Newton's laws of motion. So let's just talk a little bit about what an interaction is. An interaction is just going to be something that happens between one thing and another. So, just like a social interaction, it needs to have two people. In a physics sense, that if we talk about an interaction between two objects, we're going to require there to be two forces. So there's going to be a pair of forces that are acting. So if you were to push on the wall, then we might call that an action force. And what's going to happen is that there's going to be a reaction. The wall is going to push back on you. So we're going to call that a reaction force. There's going to be a pair of forces happening when there's interactions between one object and another object. This pretty much leads us into Newton's third law of motion that says whenever we have one object that exerts a force on another object, then the second object is going to exert an equal but opposite force on the first object. And I'm just going to say that this is going to be equal in magnitude, equal in number, but opposite in direction. So if I were to go ahead and push against a block, and I pushed with a force of 100 newtons, then what Newton's third law says, it seems pretty obvious, but the block is going to push back on me with a force of 100 newtons. Kind of another way to think of it is I can't touch this block without the block touching me. So just kind of in text, what I said on the first slide is these forces actually have names. There's going to be an action force, and then there's going to be a reaction force. And pretty much the force that's starting it all is called the action force, and then the force that reacts is called the reaction force. Kind of something that's interesting is neither force can exist without the other one. For example, if there's nothing to touch, then there's no reaction force to be had, and if there's no action force, there's not going to be any reaction force. Again, equal in strength, magnitude, and opposite in direction. And kind of the tricky part of Newton's third law is it's always going to act on different objects, and I'll talk about that in a little bit. So let's just kind of consider if you're on perfectly frictionless ice. So this is going to be you, and there's absolutely no friction, so as much as you try to put a force on the ice, you simply can't do it. If this was some rough ground, just like that, then you could apply a force on the rough ground, and the rough ground could apply a force to you, and you'd be able to move. But that's not the case. We have perfectly frictionless ice, so the only way to possibly move is if you were to have a physics textbook, and if you were to take this physics textbook and throw it in that direction right there, then you're applying a force in this direction, and then the book applies a reaction force in this direction, and you are able to kind of move off to the side. We can kind of re-express Newton's third law to say for every action there's going to be an equal but opposite reaction. For example, if we had a car on the road, and what's going to push the car forward, you might be asking yourself, and you might be saying the tires. Well, it's actually the road pushing the tires forward. What's going to happen is the tires are going to push that way on the road, and the road is going to push this way on the tires. So this would be my action force, and that would be my reaction force. And it's actually the reaction force that makes it move, because the action force occurs to the road, the reaction force occurs to the car. So different objects. So just a little bit of practice. Suppose we have a rocket, and I have a pretty cool rocket demo. The action force is going to be the rocket pushing onto the gas. The reaction force is going to be the gas pushing on the rocket, and this is going to be the force that makes the rocket go forward. The action force is going to be this force right here. If you ever see a problem that asks about action-reaction force, it's always going to be the same number. Okay? So if a soccer player kicks a ball with 1500 newtons worth of force, then the ball is always going to push back with the same amount of force, so it's always going to be 1500 newtons. It's never going to be slightly less, it's never going to be slightly more, it's always going to be 1500, or the same number. So this is going to be where it gets tricky. Suppose I were to have a table just like this, and I were to go ahead and set a block on this table right here. So this is going to be my block, or maybe my physics textbook. And let's just kind of identify the forces that are going on right here. You're going to say, okay, this is going to be the weight of the block, and we know that the table is going to support it, so this is going to be the support force. And the question is this an action-reaction pair, where that's the action and that's the reaction? And you may say to yourself, yes, of course, they're equal in number but opposite in direction, but no, they don't make up an action-reaction pair. Why? Because they occur on the same object, right? And we know that Newton's third law says that these forces have to act on different objects. So we have to kind of ask ourselves, if this is the action force, which it is, then where is the reaction force? Now it turns out that this table is going to be on Earth, and if the Earth pulls the book down, then the book is also going to pull the Earth up. So this is going to be some reaction force, which is going to be acting on a different object. So the weight of this object is going to pull the Earth up ever so slightly. Now it turns out, because the Earth is really massive, and this guy is really not so massive, yes, the Earth does feel a force upwards, but it doesn't accelerate because it's got a big, huge mass. So take a second and ask yourself, if we have a cannonball system, Newton's third law says that the force on the cannon must be the same as the force on the cannonball, equal in number, opposite in direction. And how come the accelerations are different? Well, remember that force is equal to mass multiplied by acceleration, and very simply, the cannon is much more massive than the cannonball. So even though they experience different forces, the acceleration of the cannon is much less than the acceleration of the cannonball. So let's just kind of talk about the cannonball example just a little bit. Newton's third law says that they both experience the same force, but the cannonball is not very massive. The cannon is very massive. Therefore, the acceleration of the cannonball is relatively large. The acceleration of the cannon is relatively small. So the same force on the small mass is going to produce a large acceleration. The same force on a large mass is going to produce a small acceleration. One kind of thing that's tricky about Newton's third law is going to be kind of defining what the system is. Suppose we have this orange, and we're going to say that our system is just kind of this dashed line. Then here we see an external force on the orange, and so we would expect it to be accelerating. So we would expect it to be accelerating. Inside of the system, there are forces involved, but we do not care at all about these forces. If you think about it, the cart's pushing the orange forward, the orange is pushing back on the cart. These are action-reaction pairs, but we don't care about them. They are inside of our system. Just like we could say, I have this ball right here, and this ball is going to be my system. Then yes, there are forces inside of this system. There's a bunch of molecules that are in this ball, and they're all kind of bound together, and there's forces going on and fun stuff like that. I don't care. They are inside of my system, so they're not going to cause any accelerations, just like that force and that force are not going to cause any accelerations. What is going to cause an acceleration is going to be that force right there. Now we can kind of see what's causing this action force right here. It's actually caused by this guy right there. And keep in mind that action and reaction forces don't cancel because they act on different things. So it's the external force by the apple that's going to cause the acceleration of the orange. Now we can take this a step further, and we can say, well, what would happen if we defined our system to enclose both the apple and the orange? So you kind of see that now my system is going to be inside that. Well, now this force is inside the system, and it's not going to cause an acceleration, so relative to Mr. Apple right here, Mrs. Orange is not accelerating. So action and reaction within the system are going to cancel. And as long as there's no external forces on the system, then it can't accelerate. So how is this system, even moving? Well, what makes this system move is well, we have to look outside of our system. There has to be some other force that are acting, and we know that the apple is pushing on the floor, right? Just like kind of see right down there, the apple is going to push on the floor, and the reaction force, which is going to be external to the system, is going to be the floor pushing on the apple, and of course this is due to friction. So to an outside observer, this is going to be an accelerating system. So this action-reaction pair occur within and without the system, and so they're not going to cancel. So think about having two people with the same mass on some perfectly slippery ice, and they push off on one another. Well, they both move at the same speed in opposite directions. Now, this one's kind of tricky. Suppose I've got my two people, and person A pushes on person B with 50 newtons, then person B has to push back with 50 newtons worth of force. If this guy pushed with an extra 100 newtons worth of force, then then this person also pushes back with 100 newtons worth of force. So it doesn't matter if they both push equally or not, because one pushes on the other has to push back with the same amount of force. So they will always move at the same speed in opposite directions as long as they both have equal mass. The forces have got to be the same. Now this slide right here just kind of has the summary of Newton's 3 laws of motion. The first one is inertia, that says an object at rest is going to stay at rest unless acted upon by an outside force. The second one essentially says force is equal to mass multiplied by acceleration. And we kind of have the third one right here that says if there's an action force, then there's going to be a reaction force that is equal in number and opposite in direction. Now just kind of a brief aside on Newton's third law. Consider the collision between a bug and a windshield, and so there's my bug and there's my windshield, and some days you're the bug, some days you're the windshield, and here we have this car kind of moving in that direction, and obviously the windshield is going to smash into the bug. One thing to keep in mind is Newton's third law says that the force on the bug has got to be the same as the force on the windshield. They will never be different. If one is 100 newtons and the other is 100 newtons. Now, what is different here is this guy is very, very, very massive, and this guy is not very massive. So this guy, much like a cannonball, has got a huge acceleration. This guy does not have a huge acceleration. What kind of happens is the bug's body simply can't take such a large acceleration, just like our bodies can't take extremely large accelerations, and that's why the bug goes flat on the windshield. It's not because the bug experiences a greater force than the windshield. That is simply not the case.